Hi, this is Dr. Chin, and this is a brief tutorial um, for how we could screen and prepare a data set for further analysis and factor analysis. Um, and this tutorial here is directly relevant to a class that I teach, which is PY 557 Psychometrics. It is a graduate level course on how to create and analyze psychological instruments. So what we're going to do in this tutorial is I'm going to walk you through how to use R and RStudio to import your data and clean up your data in preparation for further analysis later. There are some files that you need to do this analysis in this example. If you're in my class, all those files are in the Moodle page. If you are someone who is not from this class and would like to go through some of these analysis yourself, just email me and I could hook you up to the right resources. Okay, so to start off, we need to start RStudio. And if this is the first time using RStudio, I'm just going to briefly let you know what the different panes and layouts are here on RStudio. So just give it a second for it to start up. Okay, I'm going to clear everything so we can start from scratch. So you'll notice here that when you start up and you have nothing, you have three panes. On the far left, you have the console, which basically tells you what's going on in the background in terms of the analysis. And on the upper right corner, we have the global environment. And this is where we would have your data sets or your functions or your matrices being put here that we can pull from the global environment to analyze our data. In the lower right-hand corner, we see a couple of tabs here: Files, Plots, Packages, Help, and Viewer. Under Files, you could easily access your files on your computer through this handy window. Plots, this is where some of your plots may come up if you make certain plots in RStudio. Under Packages, this is one really convenient way for you to find packages on the CRAN server or install them from your local machine if you download those files ahead of time. This help window here is really useful if you need to troubleshoot or learn what certain functions are and what you could do with certain functions. And viewer is just another window here that allows you to see other things other than plots, such as graphs and other visualizations. So first off, we need to open the RMD file that I've created for this demonstration. Okay, the RMD file is the file that our markdown uses to allow you to enter your code and for it to instruct R on what you want it to do. So we're going to use data preparation example, use this .rmd. And here you see another window opening up in the upper left corner. Notice that your console is now in the bottom left corner. Now, this is for opening up an RMD file that you've already created. What if you wanted to make a new RMD file for yourself? Well, you could go to File, New File, and you could do R script or R markdown. I'm teaching my students how to work with R markdown. Name it whatever you want, put your name in, and you could tell it what would be the default output format. This is one of the reasons why I use R markdowns, because you could have RStudio basically create a single file that is in HTML, a PDF, or Word that has all of your code, including all the output that came from your code. And that way, my students would only need to submit one document for grading. So click Word, click OK. Notice here that there is another tab here named Untitled. and it has some explanations here as to what the markdown document is. And it has the title, author, date, and the output here at the very top. Notice that it is still untitled, so you probably still need to save it if you wanted to save this as a markdown folder for you to open again next time. So I'm going to close this out, go back to the R markdown folder that I have over here. So first we want to set the working directory. This allows R to know where to pull data from. And typically, this you shouldn't have to do this if your if your RMD file is in the same folder as your data set. But as just good practice, I like to make sure that we're pulling stuff from the right directory here. So in this case, we're going to set the working directory. Notice the function here is set WD, open parentheses, open quotation mark, C drive. And this is the pathway for where my file is located at. Actually, let me check. This may be the office computer here. No, okay. So it is not in this path. So maybe this will be a good chance for me to show you how to change it. Because you'll need to change the path for wherever your files are located at. Okay. So I would click on really any of the files in the folder where it's going to be my working directory. And since I'm using a Mac, it is right click and get info. If you're using Windows, it's right click and properties. And it tells me where this file is located. In Windows, I think it's gonna say a location, and it'll give you the path folder. Copy and pasting this here so I can make modifications. So notice here that it has C drive. For Mac, I don't usually include the C drive. And the nice thing about Mac is that it gives you the path with forward slashes here in between the folders. Now in Windows, I believe it gives you the path with backward slashes. So just FYI. And notice too that we have to end with another forward slash. Like this doesn't have another forward slash. So we need to add that in there. So I'm just gonna copy this, put it right here. Okay, I'm gonna run that. Now to run it, you press Command and Enter together at the same time. If you have other code in the same chunk, by the way, I've not really explained what a chunk is. A chunk is basically the part of the markdown document that contains the code for you to run. If you wanted to enter a new chunk, just go to the white portion of the document and then click Insert, click R, and there you have it. You have another chunk. Make sure to not enter your code in the top, in the first line and in the last line where you have this dot thing. Okay, so I'm going to highlight this. I'm going to press Command Enter, and for Windows it is Control Enter. You could also press Display button that runs the current chunk. There are a couple of other options here at the very top. You could say Run Selected Lines, Run Current Chunk, basically all the lines in that chunk, Run Next Chunk, Run Setup Chunk, run all the chunks above and run all the chunks below, or run everything. I typically like to run it line by line. That way I know what functions exactly am I asking R to do. So I'm gonna run this. Notice here in the console, it now has my code, and it is now ready to enter the next line of code. If there are any error messages, you'll see them coming up over here in my console. So I like to look at my console to make sure that everything went okay. Usually the error messages are in red, but sometimes there's instructions in there just to let you know what it did in red, and it still works out. All right, so I set the working directory. So now R knows where to pull the data from, specifically my computer. So my next step is to use the read.csv function to pull my data set. And my data set is ds data-ec.csv. Note here the open parentheses and the closing parentheses, as well as the open and closing quotation marks. I'm naming this master. You don't need to name this master. You can name this whatever you would want. But I'm just naming it master. So read.csv, name of my data set. I'm calling this master. This is going to import the file into the global environment. So notice what pops out over here when I run this code. It's my data set. It has 355 observations, 26 variables. Typically, I like to double check that is correct. So this is my data set. If I open it in Excel, it has a true Z in terms of the variables. So that is 26 variables. And it has how many rows here? All the way to 356 rows. The first row is the variable. So that means we have 355 respondents. Minimize that. So that seems about right. Oops. That seems about right. 355 observations and 26 variables. Now we can use the summary function. So just type in summary, all lowercase, to figure out the descriptives. So notice in here that we got, for example, for Q1. And by the way, the data set is basically 3 categorical variables: gender, level, and advising. And items 1 through items 23. Data coming from a questionnaire. The note here, the minimum and maximum values, I like to look at that because just in case someone did enter data that is out of the realm of possible data. So for example, in this 23 item questionnaire, it is a Likert scale that gives people a response choice between 1 through 7. So you really shouldn't have any values that are more than 1 through 7. Sometimes you may have values that are within that range, such as 2 through 6, or 3 to 7. But as long as you don't have anything that's more than 1, less than 1 and more than 7. It also gives you the first and third quartile, the median and the mean. Gives you the number of missing data. So NA stand for missing data. I typically like to eyeball this just to make sure everything seems about right and there's nothing egregiously wrong with data over here. So it looks good. The view function, and notice that V is capitalized. View function allows me to view my data right here, just like how I would see it in Excel. And by using the names function, it lists the variable names: gender, level, advising, Q1, all the way to Q23. So now that I know that I've imported the right data set and everything looks about right, let's examine some missing data patterns. Now to do this, there are 2 packages that I want to install: Baylor at Psych and MMLD. Now R as a program comes with its own default sets of packages that you could use for your analysis. And so sometimes you need to download packages to run more specific types of analysis. So if you wanted to say run the omnibus multivariate tests for missing completely at random mechanism, basically Little's MCAR tests, we would need these 2 packages here, Baylor at Psych and MMLD. So to install them, unfortunately, these 2 packages are no longer found on the CRAN mirrors. You need to download the older versions of those packages that are no longer being maintained by CRAN. So the steps here are a little bit complicated just to install these libraries. So what I did was I've downloaded the packages themselves, known here in my folder as Baylor at Psych, as a tar file, as well as MMLD. Typically, if you have a package that is hosted on the CRAN mirrors, you could do install packages, open parentheses, Baylor at Psych. If you were to do that, it's not going to work because it's no longer found on the CRAN mirrors here. So what I'm going to do instead is I'm going to use this nifty point-and-click function here. Go to Packages and go to Install. And by default, it's going to say repository in your CRAN servers. I'm going to pick package archive file and tell it where the file is. Okay. So let's do Multivariate site first. Install. All right. Notice that it's done. Everything looks about right. No big error messages. Once I have the package installed, I need to load it. So the nice thing about installing packages, I believe, with most R programs is once you install it, you don't need to reinstall it again. You will just need to load it again using the library function. And looks like that went well too. Now, I have a note over here for those who are using Windows. For Windows machines, you may encounter an error stating make not found. What you need is you need RTools 40 to build R packages that you see a C++ or Fortran code from the source. So go to this website. Remember, this is only for those who are using Windows. That's this extra step that you need to do. Download the appropriate installer. Either it's a 64-bit or 32-bit. If you're using Windows 10, it's probably going to be 64. Download it. And after installation is complete, you need to perform one more step to be able to compile R packages. You need to put the location of the RTools make utilities on the path. One way to do this is to do it in R. So basically, copy and paste this code into your R Markdown folder. I mean, R Markdown document. This is what I have right here. I'm not going to run this because I'm using a Mac, but I'm just telling you what you should do if you're using a Windows. And then restart R, verify that the make can be found by running the function sys_system.which. If you run that, you should see a path come up in your console that looks like this. If that works, you can now install Baylor at site from the source, going back to step number 1 again, trying to install it from your local machine. So once you're done with that, and we want to install the MMLD package as well. So again, I have it here on my local machine. MMLD install. And again, technically I don't need to do this because I already have it installed, but I'm just showing you how it looks like for you to do it on your own. So done, looks good. I'm gonna load the MMLD library. All right. So now we're ready to run Little's MCAR test and interpret the results. Type in little MCAR, L is capitalized, MCAR is also capitalized, everything else is lowercase, and the name of your data set, which is, in my case, master. We'll let it run for a little bit. Notice here that it has a stop sign. That means it is thinking and processing and crunching the numbers. What is going on here in the background is it is taking the pattern of taking the missing data patterns that is observed in your data set and comparing it to the missing data patterns that come from a data set that has missing data that is missing completely at random. If there's a really low chance that your missing data patterns is coming from that type of data set with that type of missing data distribution, then we would need to decide what to do with it. So in this case, the p-value is 0.06. So there is a 6% chance that our missing data patterns is coming from a missing completely at random missing data mechanism. So that's more than 0.05. So we would retain the null hypothesis and say that our data is missing completely at random. Now, if this was less than 0.05, then we would have to say that the data is not missing completely at random, because we need to reject the null hypothesis in that sense, in that case. So because P is more than 0.05, Little's MCAR test is not significant. Missing data appears to be missing completely at random. So that's a good thing. Next one we want to do is we want to start carving out a data set in preparation for multiple imputation. First, we need to make a function to calculate the percent of missing data that we can use across rows for people and across columns for variables. So let's call this function percent missing. Percent missing equals to function, open parentheses, x. This is the name of the function referred to here. X is basically whatever variable level or participant level you're applying this to. Sum of the missing number of missing data divided by all the data within that variable or that person times by 100. So that should give you a percent missing. And notice here that the function comes up here in my global environment. So first we want to apply this custom function to make a table of percent missing across rows, so across people. So basically what we want is a variable that tells you the percent of missing data for each person. So imagine, that we're adding a new variable. So instead of 26, we have like a 27th variable. We're not really adding the variable per se, but at least in RStudio, it recognizes it as another variable. So the function here is apply, open parentheses, master, open brackets, space. This space is crucial because this tells R that you want to apply this to every single row of people, comma, negative C, open parentheses 1, 2, and 3. What this means is we are removing columns 1, 2, and 3. Because remember, columns 1, 2, and 3 are categorical variables. This is gender, level, and advising specific to this data set. Close parentheses, close brackets, comma. 1 means we're applying the function to rows. If this is 2, then we're applying the function to columns. We'll do that later, but for right now, we'll do for rows. Percent missing is the function. So apply the percent missing function across rows for all people except for columns 1, 2, and 3 in this data set called master. And we are going to name this basically matrix of data as missing. So that's all what this second line of code is doing. Missing equals to the exact same code as above. And let's make a table for this variable. So the way to read this is there are 266 individuals with 0% missing data. That's a good thing. There are 6 people with 4.34% missing data. So you always want to read these numbers here as percentages. 1 person has 13.04% missing data. 2 has 17.4% missing data, and so on and so forth. We have 70 people with 100% missing data. So we definitely need to exclude these people before we impute data because we don't want to just make up entire gobs and gobs of data. But more specifically, what we're going to do is we're only going to impute data for those who have missing data that have equal to or less than 5%. So we need to start carving out a data set. So master is our data set. Open brackets, missing less than or equal to 5. That is referring to this variable that we just created here, comma. The space means we're applying this to all columns. So basically what this means is we want to create a new data set, a sub data set called replace people. And we're calling this, we're pulling this only from individuals who have missing data that is equal to or less than 5%. So notice here that we have a subset data set called replace people. And now we have only 272 observations. Now you probably want to double check that the numbers here are right, that you've only excluded 70 plus all these people, except for these 6 people. So we're only imputing data for 6 people. Everybody else has more than 5% missing data. Next, we want to create a data set that selects rows, so participants who don't meet criteria for acceptable levels of missing data. So now we're switching this to missing more than 5, and we're calling this don't people. You can call this whatever you want. Now we have 83 observations. If you take 83 in this data set plus 272, that should be 355. So double check that. That looks right on your end as well. Next, we want to apply the same function of percent missing to rows. Notice that this is now number 2 as opposed to number 1. Everything else is about the same because we're applying it to everyone except for rows 1, 2, and 3. We're calling this variable missing 2 so we don't confuse ourselves. Let's make a table out of it. So we can see that 19 variables has 0% missing data. 2 variables have 0.36% missing data. And 2 people have 0.74% missing data. And notice that we're applying this to the replace people data set. So this is from the sub data set that we've already excluded those who have unacceptable levels of missing data. So we want to create a data set called replace column from the replace people data set, except for columns 1, 2, and 3. So in this example, none of the variables have more than 5% missing data, as shown over here. So we're only going to be removing the first 3 columns because they're categorical variables. If you do have other variables that have more than 5% missing data, you want to make sure that you exclude them over here. So now we have a replace column. Notice that now we have 3 less variables, but same number of participants compared to the replace people data set. And we also want to create a data set that selects the columns that do not meet criteria for acceptable levels of missing data. In our case, we don't have any, but we did exclude columns 1, 2, and 3. So we're going to create a sub data set that only has those columns for all people. And that's called the don't column data set. Why are we doing this? Because we're going to put all the data sets together potentially so that we have a more complete data set at the end of it. So now that we've parsed it out into the don't column, don't people, replace column, and replace people data sets, we are going to install the mice library. So for this one, CRAN is still hosting this package on its CRAN servers. So you can use install.packages and open parentheses, open quotation marks, mice. So I do that. So for the sake of demonstration here. So they downloaded the binary packages into this folder. Now I'm going to use the library function to load that library. There you go. Next, we want to run mice to conduct the multiple imputation on the replace column data set. Because remember, the replace column data set only has people with acceptable levels of missing data and only has the variables that you want to impute data for. The reason why we are excluding the categorical variables is because mice doesn't do really well with categorical variables, only continuous ones. So complete is the function to run the multiple imputation. Open parentheses, temp no miss. That's basically the function, or at least the temporary data set that we'll be creating. And actually, hold on. I think I skipped a function here. Sorry, my bad. So we're going to use mice as the function to do the multiple imputation on the replace column data set. And we're going to call this temp no miss. Run that. So it has created 5 data sets that are multiply imputed. And next we're going to instruct mice to select one data set to be imputed so that we can use it for our analysis. Now technically in multiple imputation, there's the third step of averaging your results after running your analysis on all 5 data sets. But just for the sake of this demonstration, we're just going to pick one of these data sets. So the command here is complete, and we're referring to the temporary data sets created over here. And you can put any numbers between 1 through 5. Just pick one at random. And we're going to call this no miss, as in no missing. You can call it whatever you want, but I'm just going to call it no miss. So check that all the variables are imputed. If I run the summary, you'll see that there's no missing data. Questions 1 through question 23. These are the variables. Questions 1 through 23, because remember, we excluded the categorical variables. We can compare this with the original data set. So notice we had the NAs in the original data set. Now we do not have the NAs. Now, if you did remove columns that had more than 5% missing data from the replace people data set, make sure to bind those columns back into your data prior to moving to the next step. So below here is an example using the cbind function. So cbind is basically binding columns for the don't column data set as well as the no miss. So remember, the don't column contains only 3 variables for all 272 observations. So we're combining this together with the no miss data set so that we can have 26 variables. And we're going to call this filled incomplete. Now, in this case, I don't really care too much about those three categorical variables. So I'm just going to move forward and work with the no miss data set. All right. Next, we want to identify multivariate outliers. And we're going to use the Mahalanobis index. So the function here is Mahalanobis, open parentheses, no miss, because that's the data set that I want to use. That's the one that's been imputed. We're going to pull all the column means, and we are going to pull the variance covariance matrix from the from this data set here. NA.RM equals true, as well as the use equals to pairwise. That's only relevant if you have missing data. That's just to show you what you would do in case if you do have missing data in your data set. So Mahalanobis values basically for everyone based on the column means as well as the variance covariance matrix. And we're going to name this variable Mahal. Let's run this. If you just type in Mahal, you should see the Mahalanobis values for each person. Now that's not really useful. So let's get a summary instead. Minimum is 1.383, maximum is 95.69, mean is 22.916. Let's calculate the cutoff score for p less than 0.01 because we only want to exclude multivariate outliers that have a p-value less than 0.01. So the function here is q, CHISQ, also chi-square, q chi-square, open parentheses 0.999. That's basically 1 minus 0.001, comma. And the degrees of freedom is basically the number of columns, or the number of items in your questionnaire. So ncol is pulling the number of columns from no miss. And we're going to call this variable cutoff. So the cutoff is 49.73 based on the p-value as well as the number of degrees of freedom, which is 23. So any Mahalanobis values more than 49.73 are people whom we will want to exclude. So let's see the number of people who have Mahalanobis values less than a cutoff score. We only had 245 people who have Mahalanobis values less than a cutoff score of 49.73. You want to exclude these 27 people here. So remove the multivariate outliers. That's pretty easy. Just name the data set, open brackets. Those with Mahalanobis values less than a cutoff only in terms of rows, comma. And notice here that there's a space because this applies to all columns. Close brackets. Let's call this a no-out data set. So the no-out data set now should have 245 observations, 23 variables. That is 272 minus 245. That is 27 people that we excluded. So now that we have excluded the multivariate outliers, let's examine the multivariate assumption. We're going to do a couple of things here. We are going to run a statistical test to see what's the likelihood that our entire data set, questions 1 through 23, meets multivariate normality. Now, I will say this is not the greatest test. I haven't had a chance to find a better test that is calibrated appropriately, because I think this test tends to produce too many false positives. So pretty much every test is going to be statistically significant, unfortunately. But what we're going to focus on here is the visualizations. We're going to make a normal QQplot and a multivariate normal histogram, so we can actually see how the data is distributed. So for the statistical package as well as for the QQplot, we need the MV norm test. So to install it, again, you go install the packages. It's going to pull it from the CRAN server. Let's load it up. And we need to transpose our data set because this test requires the rows to be variables. So T is the function here, it's in transpose. No out, and let's just call this this data matrix M. You can call it whatever you want. And then we're gonna run the multivariate normality test. In this case, supposedly the Shapiro test. You can see that here the p-value is statistically significant, which means that there's a really low chance that our data set is coming from a multivariate normal distribution. But let's take a closer look at the QQplot. What the QQplot does, and the function here is QQnorm, and put in your transpose data set. What it is that it plots your quantiles from your data set with quantiles coming from a multivariate normal distribution. And what you want is for your data to be to meet along an imaginary diagonal line over here. And we can see that we are not following this imaginary diagonal line, because if your data set is coming from a multivariate normal distribution, it should be converging over here in the diagonal. So 2 is 2. Sorry. All right, so let's see if we could plot a multivariate normal histogram instead. For that, we need the R companion package, and you can use to install packages. R companion, run it, load it up. The function here is plot normal histogram. Notice that N is capitalized and H is capitalized. No out is the name of the data set. And prop is true. You can take this away too. It just changes the y-axis slightly in terms of if it's a probability versus a frequency. So we're just gonna leave it there. It's gonna give you the same similar type of distribution. So we can see here that our data is actually positively skewed in a multivariate normal sense. So you have a couple of options here. You could transform the data to make it more multivariate normal. You could try to move ahead, and if you're running a factor analysis, make sure that you're using the right estimator that is robust towards multivariate normality. Maximum likelihood, for example, doesn't do really well if your data is not multivariate normal. Weighted least squares does better if you have validations in multivariate normality. Now, if you wanted to transform your data, you could, and I'm just going to show you a couple of ways in which you could do it. I don't typically like to do it because it makes the interpretation of the raw coefficients a little bit difficult to interpret, or to explain at least to your reviewers or your readers. So I like to keep the raw data in their original metrics. But if you wanted to say use the square root, so we could the square root is a nice transformation for data that is slightly positively skewed. So our companion is the package that you need to do this transformation. SQRT is the name of the function. This is the name of your data set. Let's transform. Let's basically do a square root transformation for data in your no out data set, and call this square root underscore no out. And you can call this anything that you want. And to do the multivariate normal test as well as the QQplot, we need to transpose that transform data set. According to the test, it is statistically significant. That means we need to reject the null hypothesis. Let's take a look at the QQplot. It looks a little bit better compared to before, but let's take a look at the multivariate normal histogram. So a little bit better, but still not really normal in terms of multivariate normal distribution. So you sort of have to decide in your mind, is it worth the transformation? Because you do lose that ability to make more intuitive interpretations of your parameter estimates versus making it multivariate normal. Because the data is still positively skewed, let's try to use a logarithmic transformation instead. This is typically for those that is more extremely positively skewed. We're going to add a constant of 5 over here so we don't have too many zeros in the matrix. When you take a log out of numbers that is coming from a Likert scale ranging from 1 to 10 or something, you tend to have a lot of zeros. So we're just going to add 5 so we don't have that many zeros in here. So the function here is log no out plus 5. So we're adding 5 as a constant. And we're going to call this data set log no out. We're going to transpose that data set, run the multivariate normality test. It is still statistically significant. The QQplot here, again, looks better compared to the first one, but I don't know if that's much better compared to the square root transform data set. Let's look at the multivariate normal histogram. It's still positively skewed. So it doesn't seem like we can fix this problem of non-multivariate normality. So we may consider moving forward with either one of these transformations if you would like, or use an estimator such as weighted least squares to account for this normality if you're doing an EFA or CFA. Another note here is if you have data that is negatively skewed, if your data is piled up on the right side of the distribution, what can you do? Well, first you want to reverse score them, basically. You want to reflect the variable. And the formula over here is basically the maximum value of your, say you got a response choice of 1 through 7. Take the maximum value of 7 plus 1 minus each person's scores. So in this case, it is 7 plus 1, so 8 minus the values of each person from the NOAA data set. Remember, recall that space means we're applying this to every person, and we're excluding columns 1, 2, and 3 because those are categorical variables. So 8 minus everyone's values here for all the columns. So you could do that if you wanted to, and then after you reflect your variable, transform that variable using whatever transformation that you would like. All right. So this here is an example of the write-up. We got a sample of students, 355 students. This is an instrument with a 23 item Likert type scale, where they indicate the level of agreement or disagreement to a target statement. Little's test for MCR was not significant, so you take this information from your output, suggesting that the missing data pattern was missing completely at random. This is the missing data pattern that's coming from the tables that we have made. All 83 participants with more than 5% missing data were discarded before imputation. This left us with a total sample of 272 individuals. Missing data for all participants were imputed using multiple imputation, using the MICE algorithm in R. And we're just going to basically describe what is multiple imputation. It's one of the best ways to deal with missing data. All the variables were used for the imputation, as in those 23 items. Then we look for multivariate outliers. Mahalanobis values were calculated to identify outliers. A total of 27 participants were identified as outliers based on p-value less than 0.01 and this amount of degrees of freedom, which is 23. These participants were discarded, leaving us with a total sample size of 244 people. We then looked for, we then examined to see if our data set in a multivariate sense met normality assumptions. We ran the Shapiro-Wilks test for multivariate normality. It indicated that the data was not multivariate normal. Visual inspection of the multivariate QQplots and a histogram suggested that variables were positively skewed. A square root and logarithmic transformation was done, and this provided similar results as well. I mean, basically the data was still positively skewed. Future exploratory or confirmatory factor analysis should use estimators that are robust towards violations of multivariate normality in this case, such as weighted least squares and maximum likelihood with robust standard errors. So once you're done with this, if you're one of my students, I would want you to create a single document that has all of the code and all the output for this. But before we do that, our markdown doesn't do really well if you have the code install.packages in your line of code. There's a way to go around this, but I've not figured out how to do that yet. So I'm just going to remove all the lines of code that has install.packages. Okay, so to create that one document that has all of the code and the output, you want to click on knittoword, and notice that he's trying to run all the code and to put it together. So it's basically rerunning all the analysis and putting it all into a Word document. It may take a couple of seconds here. So notice that it is running. It has the stop sign here. So it's visualizing the data, because I think we use the view function in there. So we're still thinking. There you go. Okay. Starting Word up, because I've asked it to output as a Word document. Sweet. Okay, so it has the title, the author's name, the date, and these are my sets of codes. Notice that it very nicely mirrors the chunks for my code, as well as the output for the respective code. So it'd be really easy for people to see what you did and what you got out of the analysis that you did. So once you get this Word document, make sure you save it. Click Save As. I think I already have a document. Let's just replace it. Blah, blah, blah. Yes. Not be saved. Okay. So if you run into that issue, just save it under a different name. Let's call this 2. I don't know why it does that. I think it's just a glitch in our markdown. And there we have it. So that's how you work with R in RStudio in screening and preparing your data set for further analysis. I hope this video tutorial was helpful, useful to you. Let me know if you have questions. Feel free to reach out if you need to have access to any of these files and documents. And yeah, that's it. Have a good rest of the day. Take care.